Last time we said that for certain permutations W avoiding the patterns 3, 4, 1, 2, and 4, 2, 3, 1, there's a matrix A such that evaluating any trace at the Kaiserstein-Lustig basis element CW is the same as applying the corresponding immanent to the matrix A. Now the matrix A is the path matrix of a certain planar network called a zigzag network, or in the special case, a descending star network. So let's look at these. Okay, remember for a planar network D, Z of D is the sum of all types of path families that cover D. And my claim is that if W avoids the patterns 3, 4, 1, 2 and 4, 2, 1, 4, 2, 3, 1, then there's a planar network that I'm going to call FW, such that Z of FW is the Kaiserstein-Lustig basis element indexed by W. The proof of this claim is kind of long. It's mine, but it's kind of long and I don't want to bother you with it. It's in my paper on the syllabus that has 3, 4, 1, 2 and 4, 2, 3, 1 in the title. So the idea is this: the planar network comes from a bunch of stars, and the stars are arranged so that they go down to the right and then down to the left and then down to the right, down to the left arbitrarily many times. They could also start at the upper right and go down to the left first and then down to the right and then down to the left, etc. So here's a small example. As you can see, even to show a small example, we need, so I use 10 sources and 10 sinks. So this arrangement of stars is not exactly the planar network, but the planar network is based on this. So what we do to get the planar network, this is going to be FW over here. So I just copied the stars, but I'm going to look between consecutive stars, and if I see two paths from the central vertex here to the central vertex there, I'm going to smush them down into one path. So I can see two of those right here. So I'm going to get rid of them and replace that with one path. And then between this star and that star, I see the same thing. There's two different paths from this central vertex to that central vertex. So I'm going to get rid of them, replace that with one edge, which is going to be shared by two paths. Now from this star to that star, again, there's two paths from the central vertex on the left to the central vertex on the right. So I'll get rid of them and replace that with one path. And here there's actually three paths from the central vertex on the left to the central vertex on the right. I'll get rid of all three and replace them with one path. I guess I'll get rid of the outside too. And leave the middle one. So there we have it. This is what I call a zigzag network. All right, now what is W? W is not the permutation that you get by going straight through all of the intersections and seeing where each path ends up on the other side. It's a little more complicated than that. To get W, we have to look at consecutive stars, and then, so each star corresponds to an interval. Here 7 to 10 and 6 to 8. For every pair of intervals of consecutive stars, we're going to add a new star which corresponds to the intersection interval between them. So we're going to put a new star right here. And then connect the stars that way. So this can go all the way across, that can go all the way across, this can go all the way across. Now, between these two stars which overlap, we'll put another star on that intersection interval and connect them that way. Between these two stars which overlap, we'll put a new small star on that overlap interval. And now these two intervals intersect in an interval of length 3, so we'll put a size 3 star right there in between them. Alright, so now we're done putting these intersection intervals in between the bigger intervals. And now we're going to look at the path family that goes, every path goes straight through every intersection that it's in. So let's write this down. W equals, so path 1 goes up here, and then down, and then up, and then down, and then up, and ends at 7. Path 2 goes up a little bit, straight across, up a little bit, up, up, and ends at 6. 3 goes down and up, and a little bit down, ends at 3. 4 goes down to 1 and stays there. 5 goes down to 2 and stays there. 6 goes up to 8. 7 goes up to 10. 8 goes up to 9. And 10 goes down and up and down and up and down to 4. So that's how we get the permutation W from the zigzag network, essentially. We have to, if we start with the zigzag network, we have to put back all the stars as they were originally, and then extra stars in between consecutive stars. Now W written as a product of reversals is S14 for this star, S24 for the one I added. I'll underline all the ones I added. 25 was already there. 45 was something I added. Now I can't write 47 yet because there's other stars that come before it. 47's all the way at the end. 710 was already here. 78 was the little star I added between 7 to 10 and 6 to 8. And then 6 to 7 was the little star I added between the 6 to 8 interval and the 4 to 7 interval. Now I should mention, in case you get the wrong idea, that descending star networks don't need to be connected. Here the stars are all, the intervals all overlap each other, but stars don't need to be connected. So, for instance, if we have this planar network, that's fine. That's a zigzag network too. This is a very small zigzag that starts at the upper right and goes to the lower left. And then horizontal lines are fine, and then this is a very, very short zigzag that just has one star in it. Alright, now a natural question is, if we're given a permutation that avoids these patterns, how do we get the planar network? And the answer, unfortunately, is that there's a tedious algorithm in my paper that you can use. Again, it's the paper on the syllabus. You can look at it if you want, but we're not going to need to use it. But there is a special case in which the algorithm ends up being a little bit easier. And that's if the stars go from upper left to lower right and then they don't come back. So instead of having a zigzag, we just have descending stars. So descending star networks correspond to 3-1-2 avoiding permutations. So something like this. and then we squash down all the paths that we need to. We've got 5 sources on the left and 6 sinks on the right. So I did something wrong here. I think we should, yeah, this should go something like that. Okay, there we go. So we squish down all multiple paths from centers of stars to centers of the next stars. So if these are all going down like that, that's a descending star network. And if we're given W avoiding 312, we can create f of W as follows. First of all, we write the 2-line notation of W. Then we mark the records. Say with stars. So we'll have one, the first letter is automatically a record, and then let's say that's, well, I'm going to call it I1, and then we have I2 and WI2, and then I3, WI3. Each one of these records we mark with stars. Let's say IK, WIK is the last record. So then we draw stars for, we'll take these intervals from right to left for the reversals SIK, WIK, down to SI2, WI2, SI1, WI1. We'll draw these from left to right. And then we'll collapse multiple paths from central vertices of stars. Well, let's say to and from central vertices of stars. So, for example, let a W be the permutation 1654 723. So we write 1, 2, 3, 4, 5, 6, 7 above and 1, 6, 5, 4, 7, 2, 3 below. 1 is a record, then 6 is a record, and then 7 is a record. Those are the only 3 records. All right, then we took the 5, 7 star. 1, 2, 3, 4, 5, 6, 7, so that goes right here. And then the 2, 6 star, 2 to 6 is, what's a big star? And then we have the 1, 1 star, so that's sort of an empty star, just a horizontal line. Alright, now instead of connecting these, I can see that there's going to be two roots from the central vertex of this star to the center vertex of that star. So then I collapse them into just one path. And if we wanted, the reversal factorization of W is S 5, 7, that's the first star. Then we need an overlap star. So 5, 7 and 2, 6 overlap at the interval 5, 6. And then we have S2, 6. So this is FW. And the path matrix is, let's see, from 1 we go only to 1. From 2 we can go to any number between 2 and 6. Three can go to the same places, and so can 4. 5 goes to any of the same places, and it can go to 7. 2, 3, 4, 5, 6, and 7. 6 can go all the same places that 5 can, and so can 7. So if this is A, W, that means that we can apply a trace theta to CW by evaluating the theta imminent at AW, which is sort of an easy matrix. It has all zeros and ones. If we have a good grasp on what the imminent is, that should be pretty easy. Let's write down the zigzag networks for S3. So for 3, 2, 1, we have this star. For 3, 1, 2, we have this concatenation of 2 stars. You can see 1 goes to 3, 2 goes to 1, 3 goes to 2. For 2, 3, 1, we have the reverse of that. For 2, 1, 3, that's just this, because this is just the adjacent transposition 1, 2. For 1, 3, 2, we have something similar. And for the identity 1, 2, 3, we just have 3 horizontal lines. Now I want to show you the zigzag networks for all the permutations in S4. But I have that written down, so I think I'm going to give you a PDF file and have you look at it in the PDF file. The end.